And welcome back to Mr. Gregor's Math. Today we're talking about volumes of revolutions yet again. So in yesterday's video, we derived the formula for the volume of a cone using integration by revolving disc-shaped objects, or rather radii of discs, around the x-axis and integrating the area underneath, multiplying that by itself and pi to get the area of a circle, and then calculating the volume of the cone. It was actually pretty cool because we proved the area or the formula for the volume of a cone differently from what you would have done by dumping water from one container into another in grade 9. Speaking of containers, suppose I had a cylinder. So this is just a regular cylinder. And I had another cylinder placed within it. And this other cylinder that's placed within it, I don't know if you can see it, so I'll hold it up closer to the video. But if I turn it this way, you can see it has a green top, and there's that negative space in between. This might make what's called a bushing or a collar. So a bushing is something that you'll generally see that's packed into a portion where an axle would fit, and there'd be a small bearing inside that smaller spot, and an axle rod may go through. So this would be a way to kind of connect something to a moving rod that's happening in an engine, or perhaps something that's occurring in a wheel set, or on a piece of machinery that you're working on in a factory. By working on, I mean designing or building or whatever. And maybe you need to machine a part like this, and you need to know how much is the volume around there. Now, very simple formula when you have nice, easy objects like this, where you perhaps have just a cylinder and another cylinder. We can, of course, use our volume of cylinders formula and just subtract them. That's going to be key here because we're going to be doing subtraction of two volumes or composite volumes when we do more complicated shapes. But perhaps you're not dealing with something as easy as a bushing. Perhaps you're dealing with something more interesting. So, time to draw. Let's draw an interesting shape. I draw this shape here. I want the curvature to kind of follow, like come to an edge. Yeah, that's going to be pretty good. I'm going to assume that they have an intersection point at the top, though it's not really necessary that they have an intersection point at the top. It's just necessary that I know a beginning of the shape and an ending of the shape. And actually I'm going to draw this in a slightly different color so that I can really highlight my two functions. Okay, so think about what would happen if I took this object and revolved it around the x-axis. So if I took this and revolved it around the x-axis, it would make a weird bowl, a bowl that has kind of like a point at the tip, and then it has another inner portion that also has a point, and it comes to like a spiky edge. So it might make like a cap or a cone or an interesting bowl. I could even offset this so that it starts on the y-axis, so that it has a nice rounded edge and a nice flat portion when I rotate it, so that it actually does sit. So this inner volume right here, and I've just drawn 1/2 of the cross-sectional profile, would be repeated as it gets rotated down. And so I would have that rotation kind of looking like this. That was actually not a bad drawing. Where you could imagine this figure being spun around the x-axis and creating some sort of bowl or structure like that. Well, that's what we're going to do with Volumes of Revolutions Part 2. We're going to figure out the volume of the material that would be inside this. So a couple of things are going to be needed. This is going to be a rather interesting problem if I have this offset back, because my functions don't start at the same points. So one function starts back here and another function starts. Because we have this really irregular starting point where one thing starts here and another object starts there, it's going to be a little bit more challenging than just lining it up. So we'll actually have to do this in two pieces. We'll have to consider the volume of the revolution of just the top curve, and then the volume of the revolution from this other point A to the end of the object. Let's call that B. So we're actually going to break this into kind of two problems. My volume total is going to be the volume of the revolution of just the red curve from 0 to A plus my volume of my revolution from A to B of both the red curve and the green curve. And so I'll have to do the red curve minus the green curve. So I'll have to subtract the volume of the revolution on those same intervals. So this breaks the problem up into two pieces. Yesterday's problem would leave us with this if we had a definition of the function, and today's problem is going to deal with how to combine these two terms. So let's go ahead and give ourselves some functions so that we can actually go ahead and do this portion. So let's call the red curve something. We'll call it f. So I'm going to label red as f, and it starts up here. Let's say it starts at, oh geez, I don't know, 1, and maybe it's a radical. So this is going to be f of x equals the root of x plus 1. And I'll make it a little bit steeper radical, so 2x plus 1. And then let's make, let's leave it as just x plus 1. Let's make this green portion a radical as well too. And let's give it a name. So let's call the green portion g of x. And it's going to start at, I don't know, maybe we'll say a is, I suppose just to be easy, 1. So it's going to start at x minus 1. And it's going to go off from there. So I have to figure out this point that they go to. That point where they go to is where they're going to intersect. Now, because these, well, they might actually intersect. I think I want my intersect to be a little steeper just to verify that they are going to intersect. So I'm going to make this 2 root x minus 1. So that way there's no question in the video about whether or not they're going to have an intersection point. So I've got my two functions. My bottom function or my inner function is g of x, and my outer function or my top function is f of x. And we'll go ahead and do our revolutions now. Now from yesterday, we recall the volume of a revolution is equal to the integral from the start to the end of pi times y squared dx, where y is simply the equation of that function. So these are my functions, those are going to be my equations, and it's nice that I chose radicals because it's actually going to make it work out quite simply when I square them. So I'm going to apply this formula to each of my components. Let's take a look at the first part. So from 0 to this point A, which I'm calling 2. So my volume of just this first section, which I'll shade here. This is just a warm up from yesterday's work to remember how that works. So that'll be that portion revolved around the x-axis. That volume, we'll call that volume A, is going to be the integral from 0 to, well, I think it's going to start at 1 because that's where g of x starts. G of x starts at 1. And so this will be of pi times f of x squared dx. Now f of x is the root of x plus 1, so we'll do the integral from 0 to 1 of pi times the root of x plus 1 squared dx. And you can evaluate this on your TI-84, or actually this isn't such a bad integral to evaluate by hand, but we've done some videos on evaluating integrals by hand, so I'm just going to use my TI-84 for this. So I'll come in a little closer so you can see how to do that. I've got mine cleared, and I'm hoping that we can see this. Yeah, that's a good spot to hold it. So I'll go math 9 for integral. We go 0 to 1. Now everything inside of here is being integrated, so I'm going to use pi, so that's second function pi. Now my function is going to be squared, so it'll be the root of x plus 1, but that whole portion is squared. And dx. And so I'm hoping I can still see that on my calculator and how I've typed it. And I end up with a volume of 8.901. So this volume of A is 8.901. And that's just 8.901 units cubed. So I'll record this off to the side so that I can make sure that I've drawn it. 8.901 units cubed. And now we'll get to work on from here to here. And that's the interesting part. That's the part where we're going to take the differences of F and G. So this endpoint needs to be discovered first. I'm going to discover this endpoint by finding the intersection of F and G, because I don't necessarily know where these end. I could have an arbitrary point, like it could say that it ends just at some solid line, and that would be fine. It wouldn't change any of my integration. But if it was saying that they meet to the point and that edge is just a solid point, then I'm going to need to make sure that I find the intersection point of those two things. So my intersection point is going to be found just by substitution. So I'll have 2 root x minus 1 is equal to the root of x plus 1. I'll square both sides to eliminate the brackets here, or to eliminate the radical on this side. So it'll be 4x minus 4. I'm just squaring that to become 4, squaring that to become itself, and expanding the 4 through. And this is going to be x plus 2 root x plus 1. And I do have to be careful here because of the fact that I've got, I squared both sides. The common mistake would be to just write that it's x plus 1. But remember, when you square this, it acts like a trinomial, so we are going to have double the inner product of those two terms. Now I'll bring everything over to one side, so I'm going to have 3x minus 2 root x. I have minus 4 and plus 1, so I'm going to have minus 5 is equal to 0. And you're looking at this going, oh geez, how would I solve this without my calculator? Well, with the calculator, it'd be really easy. You just type that in as y1 and then look for the roots. Without a calculator, we've got a little trick here, because we notice that the power on x is 1, the power on x is 1/2, and the power on x is 0. So this ends up actually being a quadratic. So I can instead write this as like 3a squared minus 2a minus 5 is equal to 0. So when I read it like that, and I'm using a here as a squared is x, and so that means that a is the root of x. So now this should be able to factor. So I'm going to try it. So I've got 3a and a, and I've got 5 and 1. And I think I'm going to make my 5 negative and my 1 positive. And let's see how I did. So negative 5, yep, and positive 3, negative, yep, I think I factored that correctly. So this tells me my values of a are negative 1, which means that it's back here. So I'm not actually concerned about this particular root, so I'm not going to care about that one. So this root will be ignored. It's not that point. So this point instead is going to be at 5 over 3. But remember, a was not x, a was the root of x. So the root of x is equal to 5/3, so I'll square both sides, and I'll get x is equal to 25 over 9. So that means I need to integrate from 1, where the second function starts, all the way to 25 over 9. And you can probably tell me to do this part of my calculator because I don't want to be raising 25 over 9 to a bunch of powers, which we'll see later. So now that I've found that endpoint of my limits of integration here, I have to do that kind of fun trick where I'm going to have to integrate the top so that I can find the total area of everything under the top. And then I'm going to have to integrate the bottom so that I can find the total area underneath the bottom. And I'm going to have to subtract those two areas to just reveal what's left. Kind of like masking a room off and painting the whole thing and then pulling the masking paper off. Subtracting that leaves you with that negative image or that negative blank space. So we've got our limits of integration. We have our two functions. Let's go ahead and apply our formula. For my volume of my revolution, it's going to be basically the volume of the first revolution, from 1 to 25 over 9. And this is pi. My top function is f of x, so f of x squared dx. And I'm going to subtract my second revolution from 1 to 25 over 9 of pi. And this one's g of x. Oh, ugly brackets, I apologize for those. Squared. Now looking at this, is there anything wrong with just going ahead and performing this integration? No, there isn't. But we can actually combine these because notice they have the exact same upper bounds of integration, the exact same lower bounds of integration, and the exact same differentials of integration. So we can combine these two integration statements. And because each of them are multiples of pi, I can remove that pi as well. So my step is going to be to combine these two terms and remove pi from the integration because it's a constant. So I'll remove pi first, and then I'm going to be left with this f of x squared minus g of x squared. So I'll have f of x squared minus g of x squared. And then that whole thing is integrated with respect to x. Be really, really, really careful that you don't fall into the trap of saying that it's f of x minus g of x, that whole thing squared, because you do need to take the volumes and subtract them. If you just did that where you took the radii and subtracted, then what you would actually do is you would take this shape and you would contort it, and it would look like this. So you would be calculating a weirder volume toward there. And I know it looks like it's an equivalent area, and it is an equivalent area. But when you revolve that around the x-axis, that would create a little spile or a spike just in the middle, and it would have a very small volume. Whereas this portion here, just even probably from there to there as it revolves around, would make almost like a plate-looking ring. So it's gonna have a much larger volume when you revolve it around. Yes, it has a comparable looking area, but it's not the area we're concerned with, it's the volume. So make sure that you keep these two separate. Okay, and then now we just substitute. So we have pi times the integral from 1 to 25 over 9 of f of x squared. Now f of x was the square root of x plus 1, so that's square root of x plus 1 squared minus, and g of x was simply 2 root x minus 1 squared dx. Squaring both of these, oh, I'm running out of room here, so I am going to write back up top. Squaring the first term, it is a binomial, so I'm going to have x plus 2 root x plus 1. Squaring the second term, I'm going to have 4 times x minus 1. And you're probably recognizing this already from the expression where we solved for the intersection points. So we'll just simplify before we go ahead and perform the integration. So I have x minus 4x, so I have negative 3x's. I have 2 root x's. And I have 1 minus 4 times negative 1, so I have plus 5. And this just looks almost identical to the previous expression that we had solved as a quadratic, except for the signs are reversed. That's because we didn't care so much about the signs when we were factoring this, because we're just looking for intersection points, whereas we care about the signs when we're integrating. So now we'll go and integrate. It's probably going to be easier to express that as a 1/2 when we integrate, but let's just go through and do this here. So after I'm done integrating, it's a definite integral, so I'll have to substitute in my endpoints. The integral of negative 3x is negative 3x squared over 2. The integral of 2 root x, remember that's 2 times x to the power 1/2, is going to be 4 over 3x to the 3 over 2. And the integral of 5 is just 5x. And so I now have my integral. At this point, I've already used my calculator once. I'm going to ask one of my friendly students in class to use their calculator to evaluate this. And I'm going to evaluate it by hand because I'll wait for them to type it out and see if I get this right or wrong. I promise I will not do a jump cut here. So I have pi times negative 325 over 9 squared over 2 plus 4 over 3 25 over 9, 3 over 2, plus 5 25 over 9. So that's just going through the expression and substituting in 25 over 9. Now I'm going to go through the expression and I'm going to subtract what happens when I substitute in 1. So when I substituted 1 to the first term, I'm subtracting negative 3 over 2. When I substituted in the second term, I'm subtracting positive 4 over 3. And in the last term, I'm subtracting positive 5. So that's substituting in 1 in for each of my x values. All right, continuing on, and hopefully not making any mistakes. 25 squared is 625 times 3 is negative 1825. But I'm just actually going to simplify. The 9 squared is 81, so that's going to go into 27. So it's going to be negative 625 over 54. And it's probably going to reduce a little bit further. So 25 squared, 9 squared was 81. 27, yeah, I think that's going to be right. Now here, I'm going to take the square root first. So this is going to be 5 over 3, and then I'm going to cube it. So it's going to be plus 4 times 125. So 125 times 4 is going to be, oh, that's nice, it's 500. And then this is going to be the square root of 3 and then raised to 9. So it's going to be raised to 27 times 3 is going to be 81. And then this one is just 125 over 9. Now this I'll add my sign, so I have plus 3 over 2 minus 4 over 3 minus 5. And this is all times pi. And you can see how on a calculator free test, you're going to run into some issues with fractions, and I've probably run into some issues with fractions already myself. Now I've got to find a common denominator. Ugh. 64? No. 62. 162, I mean. I don't know. I'll probably just do it this way. What did we get on our calculator when we did that? Haven't checked that yet. But 40.522 is not the correct answer for the integral of that function that we've been working on. For the integral of that function that we've been working on, multiplied by pi, the correct answer works out to be 11.48. Which leads us to a volume of 11.48 of that portion, which is a little bit nicer in comparison because I really do think that that region likely is going to be the smallest region on that bowl, whereas the base is going to be the largest region. So adding those two things together gets me a total of 20.38. And that's in units cubed. And that's the appropriate volume. So I apologize for the mistake. And on the outtakes reel, I'm going to include the crop out of the mistake, and I'll also include me evaluating this by hand. Awesome. Join us next time on Mr. Gregorus Math when we are doing integration using trig substitutions. And don't forget to hit like, subscribe. Don't forget to ring that notification bell and check the links in the description for the merch store. They have one, and I just don't have that. Okay, so I'm going to try and evaluate this thing by hand and see if we can get to that, what was it, 11.48 or the exact value equivalent to it. So I'm looking at this and I'm going, ugh, that is hideous. So I don't want to start multiplying all these numbers by 54 because that just seems like it's going to get really, really large really quickly. So this is going to be something like 625 divided by 54. Is going to go in, I guess that's going to be an 8. So it's going to go in 11 times with 31 remainder. So I'm going to replace this with negative 11 and 31/54. Now 500 goes into 81 very similarly. Sorry, 81 goes into 500. Is it 4? 5? 5. 5 times, because that's going to be 4. 405. So it's gonna actually be 6 times. It's gonna be 486. Great. And then that's gonna leave me with 14 as my remainder. So that's gonna be 6 and 14 81sts. Now 9 goes into 125. I was right, 13 and 8/9. And while we're here, we may as well just change these to whole numbers as well too. So mixed numbers rather. And so I've got all mixed numbers now. The nice part about mixed numbers, and the only part that I actually like about mixed numbers, is the fact that I can now take these portions and add them up. Hello! Negative 11 plus 6, that's negative 5, plus 13 is going to be positive 8. Then these ones are going to cancel, and that 5 is going to make a 3. So this is pi, and this is 3. Plus, now I have 14/81. I have 8/9. 8/9 is going to be 72/81. I have 1/2, and I'm subtracting 1/3. So 1/2 minus 1/3 is 1/6. And that's going to be it for my fractions. So now I'm getting kind of closer and closer and closer to, oh, and these, I didn't record this one yet, sorry. This is still negative 31/54. So I just brought all of my whole portions together, and then I left my fractions off, and I combined a couple of them as I went. So now I'll combine these. I guess I could probably combine these easy enough too. So 6 and 54 is going to be 9, so it's going to be 9/54 minus 31/54. So I'll have pi times 3 plus, I guess that's 86/81. And then 9 minus 31 is going to be minus 22/54. And now I'm hoping that I can find a nice way to subtract those two things. I don't think I'm going to. I think I'm going to have to suffer through finding some unbearable common denominator that these things add to. I'm going to save myself some time though, and I'm going to recognize that 54 and 81 are all divisible by 9. And so that's helpful. So I'll probably be multiplying by some fraction of 9. Actually, I think I'm just going to multiply this one by 6/9. So I'll have 86/81 minus 22/54 times 6/9. Now, why did I do 6/9? Well, that's because 54 is 6 times 9. So those cancel, leaving me with, oh, I have to do this then. If I multiply by 6/9, I have to divide by 6/9. That's silly. What am I doing? I can't multiply by 6/9. Take 4. Thank you from the peanut gallery, and I of course mean that with the utmost respect. And I think I said that partway through the video too, did I not? I think I said 162. But anyways, I'll give the credit where credit's due. So 86/81 minus 22/54. These can both be written as bases of 162, so that's doubling this. So that's going to be 192. No, that's not going to be 192. That's going to be 172. And this is going to be tripled to get to 162 minus 66 over 162. And so subtracting these, I'm going to have, I think, 106 over 162. I believe that's correct. So that means that this becomes plus 106 over 162, which if I have any style in my life, that means that that's going to become over 81, and that's going to be 53/81. And that is going to be a fraction that does not reduce. So I'll have pi times 3 times, pi times 3 and 53/81. Now, I'll just pull up the old calculator and see if I got close. 3 plus 53 divided by 81 equals, hey, that's exactly the right answer. So I did manage to get to those fractions after like 25 minutes, 3 outtakes, 2 interruptions, and a partridge in a pear tree. Excellent, we're there. Fantastic. I hope you enjoyed the hour-long diatribe about one particular question.